Have you ever wondered if your measurement system is actually the source of your problems? Have you ever measured something and thought, maybe that just doesn't look right or it doesn't feel right? Well, today we're going to talk about measurement system analysis, measurement system evaluation, or what's often called Gage R&R, and we're going to dive in right now. All right, Gage R&R, measurement system analysis. What is it? Well, basically, if you are measuring parts or throughput or any other metric in your company, and you're not measuring it correctly or accurately, then you could be getting the wrong data and maybe making the wrong decisions. And that's why we need to evaluate our measurement system to see if it can actually measure the things that we want to measure. And that body of knowledge is what we call MSA, or Gage R&R, measurement system analysis. If you remember the 6 M's from Greenbelt training, you remember they are the 6 sources of variation. And one of those 6 sources of variation is the measurement system. One of the biggest problems that we have is that a lot of times humans are involved with measuring things, and human involvement always leads to variation. So let's play a little game here to demonstrate that point. I want you to count the F's on this page in the paragraph below, and I'm going to give you 60 seconds to do it. On your marks, get set, go. All right, that was 30 seconds. How did you do? Write your number down. How do you think you did compared to your neighbor? If you have other people in your company that are taking this training, compare notes, see how other people, how many F's they counted. Now, when I do this in my live trainings, a lot of times we'll get everything from, 25 F's up to 30 F's, 40 F's, and everywhere in between. And it's all over the place. And you can see just how much variation is created by humans trying to measure something or count something. Now, but you're saying, but wait, 30 seconds, that wasn't very much time. If I had more time, I could do a much better job. Okay, let's see if that's true. I'm going to give you 30 more seconds, and let's see if adding that additional time gets you a better or even a different answer than before. Are you ready? On your marks, get set, go. All right, that was another 30 seconds. Compare your notes from the time before. Did your measurement of the number of F's change? If so, then that's a perfect example of why humans cannot be trusted when it comes to measuring things. We think we're pretty good. We think we have a system and we're great at it, but we're not great at it because there's always that element of variation that's just inherent in the jobs that we do. So what is the correct answer? The correct answer is 48. If you got 48, then you got the right answer. If you got something different than that, then I'm sorry, you just can't be trusted to measure things. So we're going to have to find a new position for you here at the firm. I'm just kidding. Let me give you a couple of examples of other places where you can see measurement system variation. So employee satisfaction was measured by the team's customer service reps and by an outside consulting firm. Now, both the internal and the external folks got different results for employee satisfaction. Why do you think that is? Well, maybe when they were answering questions from the internal HR team, they were afraid to give their true answers because of, repercussions or something like that. But when the outside firm came in, they were more open with their answers. So they gave maybe a little bit harsher score on their satisfaction. Scenario number 2. These are real world scenarios, by the way. These are all things that I experienced personally in my job and in my career. So when I was working at Purple, one of the problems we had was people would come in on the day shift or the night shift, and they would measure the gap between these two glue rollers, and the gap between the glue rollers would determine how much glue fell through and was dispensed onto the mattresses when we're, gluing the different parts together. Well, day shift would come in and they're like, well, the glue rollers are completely off and we measured them and we have to adjust them. And they'd spend half hour adjusting the rollers. And then night shift would come in and be like, oh, these are off and they'd have to adjust them. Well, how much of that variation in them measuring the distance between the glue rollers was caused by the humans or the gauge that was actually measuring it, how they measured the glue rollers? So we did a little bit of a study there, and we found out that as much as 35% of the variation that we were seeing was caused by the people measuring it, how they measured it. Some people would measure right at the end of the roller. Some people would measure 6 inches into the roller. There was all sorts of reasons why the measurement was different between different people and different shifts. So once we standardized that, we found out, well, we can trust our measurement system to a certain extent, but most of the time this variation isn't real, and we can stop fidgeting with our rollers. Since we actually were able to cut back on the amount of fidgeting and adjusting and, hours literally of downtime caused by the fact that people thought the rollers were out of spec when in fact, it was just our measurement system that wasn't very good. Third scenario here. So if you're doing any of the stats training here, which you're about to do in the design of experiments portion, if you haven't gotten there yet, we're going to create some paper helicopters. We're going to drop them and see how long they stay in the air. Now, if you're measuring those, let's say you've got an iPhone and you're measuring how long it takes to have something, a paper helicopter come down and land. What could cause variation there? Well, how fast you can click the button, who's clicking the button, where they're looking from, the angle they're looking from. There's about 1 million different ways that you could get that measurement wrong. And so you'll see pretty quickly when you do that DOE training that the measurement system has a significant impact on how successful you are in getting a good measurement. We need to understand accuracy and precision when it comes to our measurements. Accuracy means that on average, are we on target? Are we hitting the middle in the example on the page here, right? So you can see that a C, for example, is accurate, meaning on average, all those darts are, right around the middle of the target, but it's not precise. Example B is precision. It is precise. Those darts are very precise, very close together, but they are not accurate. They are not on target or at the center of the target. Example A, you have something that isn't accurate or precise, so that's just terrible in both cases. And then example D, finally, we have the best example, which is what we want. We will have both accuracy and precision together, and that's what we're looking for in our measurement system. Now, why is it called a Gage R&R? Why is the measurement system analysis called Gage R&R? Well, R&R stands for repeatability and reproducibility. So Gage R&R is measuring all of the variation in the system. So what we're going to do is we're going to measure a bunch of parts, and then we're going to break the amount of variation we see in all of our data into different segments. Part of that is going to be variation caused by the parts. So this part is different than that part, right? So for example, I don't know, let me find something that I'm measuring here. A couple of sticky notes, right? We want to measure the quality of our sticky notes and how sticky they are. And this one's a little stickier than that one. So I know that there's some variation caused by the stickiness of these notes and understanding which one's stickier than the next one. Great. That's part variation. The next variation, though, is caused by the actual tool that we're using to measure it. So if we're measuring these parts using a ruler, right, looking at the ruler may not have the ability to discern, how wide the sticky note is, for example. So the actual tool is causing the problem. And then the third thing that can cause the problem is the person. So if I'm looking at measuring those sticky notes and I'm trying to measure the width, for example, and I look at it from a different angle, from over here or over here, I might see the measurement differently than my buddy next to me who can sees it from a slightly different angle. So the human, the operator, can actually cause the variation. Now, repeatability means we're going to test the same part multiple times. So I'm going to take some of these sticky notes and I'm going to measure them multiple times myself. And if I get the exact same answer every time, great. My measurement system analysis shows that I have great repeatability. Reproducibility has to do with the operator standing next to me. Can I get my buddy to also measure the sticky note and get the exact same measurement? If they can, great. If they can't, then we know that there's some operator variation in our measurement system. So what questions would a Gage R&R answer? Number one, do our operators bias the measurement? Number two, do our operators have agreement with each other? Number 3, what percentage of the variation is caused by the tool versus the person versus the actual process or the part? How much of a process change can the measurement system actually detect? This is a key question. We're going to go over that more in a minute. Can the measurement system be reproduced? Or the measurement be reproduced, and can it be repeated? And as you know, we love to rely on our software to do these things for us, so we don't have to do all the math ourselves. Thank goodness we live in a day and age where we can just click a few buttons and get the answer. So let's do it. Let's do an exercise, and we're going to perform our first Gage R&R using Sigma XL. So to do this, we're going to open up a blank sheet, and we're going to go to Sigma XL, Measurement System Analysis, and create Gage R&R study. Now, why is it called a crossed study? Why are we going to do crossed? Well, here's why. We're going to actually look at multiple operators and multiple parts. And each operator is going to measure each part multiple times. So you can see on the page here, the overlap. That's why it's called a crossed study. And these are probably the most common, the ones that I end up doing in industry the most. And the key here is we're going to have to repeat the measurements multiple times in order to get a p-value and know how much of the variation is caused by the different components. So let's go ahead and dive into a spreadsheet here. We're going to go to Measurement System Analysis, create Gage R&R crossed. And it defaults to 10 parts with 3 operators and 3 replicates, or 3 trials. We're going to randomize the parts, and we're going to randomize the operators. And then down below, you could rename your parts if you wanted to, and your operators right here, but we're just going to leave everything as is and click OK. That's going to create this massive table, and it's really handy because you can give your gauge a name, the date you studied it, who performed the study, and so on. And then in the table down below here, you can see that it has created a run order, which is, okay, experiment number 1, experiment number 2, experiment number 3. And then the standard order, which is if you were to do these in order, like have operator A run parts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then operator A repeats those and so on. That's the standard order to be running. Now, we never want to use a standard order. We always want to randomize it. So the run order is the order we're going to do the experiments. The standard order is the randomization of what we normally would have logically done, keeping things all the things together. It shows which part we're going to test, which operator is going to test it, and then it's going to put in a measurement right here. So these yellow cells are the ones you fill out. You put in the actual measurements here, and then once you're done with that, then you can analyze the study, which again, you have to go back to your measurement system analysis, and then you have to go back to analyze your Gage R&R crossed after you've created it and added in that data. Now, we don't have any data yet, so we're going to come back and do that analysis here in a second. All right, so to do this properly, instead of sending you off on a wild goose chase to go and try and do this study on your own, let's just pull up some existing data and do an analysis on that data. So go to Sigma XL, click Help, Sample Data, click through if you get a warning screen, and then scroll down until you see Gage R&R AIAG. And we're going to open that up. And here you'll see the exact same data table, except this time you've got the measurements already placed into the Gage R&R. So super simple. Now we just have to do the analysis. So we click on Sigma XL, Measurement System Analysis. This time we're going to click Analyze Gage R&R Crossed. Our data table will already be selected, hopefully, so you can just click Next. And then here, we have to move some of our data in the columns over to the cells we want to analyze over on the right. So part goes to part, operator goes to operator, and measurement goes to measurement. You can leave your standard deviation multiplier the same. Everything over here is fine. Let's see, anything else we want to put here? Yeah, multivariate X-bar R charts just to get your control charts out of it. That's not a bad thing. You can see how you perform over time. Sometimes that's helpful. Any other notes here? Nope. I mean, you can put in your titles here as well if you'd like. But that should be it. Let's just click OK. I have a fairly decent computer, but it is still having to think for a little while. So, yeah, just be patient as it cranks away at all of those numbers. And then there we go. Our Gage R&R is finished. Let's walk through this table and see what we can learn. We're going to go to our data table here. And you can see just right up the top, this is our study. As we scroll down, we do not have, we didn't put in our upper or lower spec limit, so we don't have a process tolerance here. So we can kind of breeze through that. The rest is just a summary of what we did. You'll notice an alpha to remove interaction here. So that's a 10% alpha risk there. So we do have some risk of making a decision that, something is causing variation when in fact it isn't, but it's pretty low. And then we get into the meat of the Gage R&R analysis, which is what is causing our variation in our system? Is it the parts, the operator, the part-to-operator interaction? Is it repeatability, which is the equipment, meaning I can't repeat the same measurement because for some reason the measurement system I'm using, like my ruler or whatever, isn't able to repeat it. And therefore, I can look for a p-value for each of those. And if the p-value is low, I know it's significant. So is the part causing variation? Definitely. P-value is low. That's good. We want our parts to be causing variation. We want the parts to be the main source of variation in our measurement system analysis. So low p-value for parts is good. What about operators? P-value is also low. So the operator is causing variation. That's not good, but at least we know. Is there a part-to-operator interaction where one operator is measuring the part differently for some reason? High p-value there. So we can throw that one out and say, no, it's not significant. Now, what's nice about Sigma Excel is it's smart enough to say, look, I've got a low p-value for this third one right here. So why don't we just scrap that? We're going to mark it as red. We'll throw that one out and we're going to rerun our analysis here without the part-to-operator interaction. Now, why would you do that? Well, because if you throw out your variables that don't matter, then you'll get a more robust analysis and you'll actually see the effects of the remaining factors. You're going to learn more about this in the design of experiments module. So you're going to get to that pretty soon. And when you do, you'll learn about simplifying your regression formula. So you're throwing out variables that you don't think matter. So with that variable thrown out, again, we see the part variation 0, p-value is 0, operator variation, p-value of 0. So we know that those two are definitely causes of variation, but we're not sure if our equipment or part-to-operator is causing any. So then we scroll down and we get what's called a percent total variation here highlighted in blue. This is called percent study variation, I believe, in Minitab. But the key here is we want this to be less than 30%, right? The lower this value is, the better. If it's less than 30%, we know our study is decent. If it's less than 10%, then that's brilliant. That's exactly what we want. The problem here is because of the limited number of runs that we did, even though we measured 3 operators, 10 parts, we still have a huge confidence interval spread here, which means this percent total variation could be varying anywhere from 15 to 70%. So boy, that just, that shows you that even though this measurement system analysis we're doing is useful, there's just a ton of opportunity for it to be way off. There's a chance that it could be off. So be aware of that. Now, again, we're looking at the Gage R&R, how much variation is caused by the actual, the study itself. So let me mark that in yellow. Okay. And then it's also going down and looking at the percent total variation caused by each of the different components. So this is the operator or the appraiser, 20%. Part-to-operator interaction, we know that's 0 because we threw it out because the p-value was too high. Reproducibility, it's just looking at the appraiser again, and then repeatability here, looking at the equipment, right? So again, repeatability is if I'm redoing the measurement. Reproducibility is if me and my buddy are doing the measurements, and are we different from each other versus the equipment causing the problem. So if you look at the part variation, you look at all these difference. Now this percent total variation is looking at the variation caused by this one item, like let's say the part, and it's dividing that by the total variation of the study. So actually, let's look at operator. It says the total variation that we see caused by the operator divided by all the variation is about 20%. For that reason, these are not going to add up to 100% at the bottom here. You will notice that they do not, if you were to add them up. So that's okay, because this is a ratio of this one item compared to all the variation that you see in the process. And sometimes because of interactions, you'll get, kind of like a doubling up of the amount of variation. So what can we do? We scroll down one more time and we see the Gage R&R metrics. This is the percent contribution to the total variation, and this will add up to 100%. So the cool thing here is that our total amount of variation is 100%, which is what you'd expect. How much of that is coming from the measurement system itself? Well, only 7% contribution to the total 100% here is caused by the Gage R&R. And then it breaks that down. So if you look at right here, the repeatability, this is the sum of the Gage R&R plus the operator plus the part to operator interaction. So that's looking at basically the equipment and the operator all together is how much of that contributes to the variation, the reproducibility here. Oh, sorry, repeatability, my bad. Come down here. So that number right there, you can see is that number, and that is the addition of the Gage R&R and the operator. So that is the repeatability. That is the sum of those two. So we see our repeatability here, about 3.39% is the percent contribution. And then we have the reproducibility here at 4.37%. So if we take those three numbers right there and add them up, you will see that equals the total variation. So the total variation is the sum of our part variation plus our repeatability plus our reproducibility, all three of those right there in a row. Okay. So what are we looking for? Again, we're looking for this, the part variation to be the majority or over 90%, and these to be less than 10%. If they are, great. We've got a good measurement system, less than 10% contribution. If it's greater than 10% contribution, then we got to ask, okay, how do we get our operators to be more consistent? Or how do we get our measurement equipment to be more consistent? Or the interaction between our operators, our equipment, our measurement equipment, and the parts. How do we get that to be more consistent? Okay, now let's skip over to the next tab. It pulled up some graphs for us, and these are really, really helpful. The number crunching is great, of course, but visually, if you can see what's going on, that's even better. So let's take a look at what's happening here. On the left, we've got the operator and part one, and then operator and part two. And as you scroll across, it's going to graph each of those combinations for the 10 different parts and the 3 different operators. And what does that tell us? Well, you're looking for, do any operators consistently measure higher than other operators or lower than other operators? That's something that can happen. Or are there any parts that consistently measure higher or lower? Are there any interactions between the part and the operator and so on? So if we're looking at that, operator one, part one, we can see that operator A measured this part a little higher, operator B measured it in the middle, and operator C measured it low. As we go across, you'll see for part two, same thing. A was high, B was in the middle, C was low. All right. As we go across, we start to see this trend. So what is that telling me? Well, what that tells me is for some reason or another, operator A is always measuring our parts a little bit high, and operator C is always measuring them a little low. And who knows who's right? What is the correct measurement for the part? We don't know. We just know that our operators don't have agreement with each other, which is why we see the operators as a significant part of the variation in our Gage R&R. Now, one thing you will see that's good here is, like, for example, here, part 8 and part 9, there's a significant difference between the average value measured for part 8 with this blue line here, the average value for part 9 and the blue line here. And because of that, you see there's this big gap is part to part variation. That's a good thing. We want the part to part variation to exceed the measurement system of variation. That allows us to see the signal, the change in the parts, over the noise, which is the variation in the measurement system. Then if we scoot one more graph over to the right, we're going to see our control charts. It's going to do an X bar R chart for our measurements. And this, again, is a very useful tool. And this is, by the way, the only time you want to see out of control data points, right? You want the variation in the parts to be outside of the control limits for the variation of the measurement system. So in this case, you'll notice that this first chart here is actually out of control. You have all these data points that are outside. And that is a good thing. That is exactly what we're looking for. That means we have a good measurement system. Now, when we go down to the bottom, we have the Gage R&R chart, which is our range chart. And this, again, we're looking for something here that is actually in control. We want our data points for the range or the amount of variation we see between operators and between measurements. We want that to be stable and in control. We don't want any random swings where one measurement was just way out there and caused a spike. But we do have one of those right here, operator B. If we click on that guy right there, part 4 for operator B, for some reason that measurement was just huge amount of variation there, and that's something we'd want to go look at, is why that variation was introduced there and how that happened. In conclusion here, What would we say about this measurement system? We'd say, great, we know that the operators are causing some variation, but it's less than 10% total of the total contribution of all the variation we're seeing. So for me, it's an acceptable measurement system. We could move forward. There's always room to improve and go figure out why there's variation at all and try to eliminate that, automate the entire process, take humans out of it, completely, improve the way you measure. But overall, I'd say this is a pretty decent measurement system. And that is the end of the Gage R&R module. So an exercise for you to do right now, think about some of the things that you measure and the equipment that you use to measure them. And then ask yourself, is there an operator involved? Could the operator be causing the measurement system to vary? Could it be the equipment? You're measuring weight. One of my clients was a Morton Salt, and they used scales, very robust scales to measure these 50-pound, 100-pound bags of salt. And that scale had variability in that equipment. And we had to understand how much variation was in that equipment because we were trying to get the weight of the bags to be exactly 50 pounds, right? 50.00 pounds. And if the measurement system is only accurate to, a tenth of a pound, that wasn't good enough for us. We had to be better than that. So it was really important that we understand how much that equipment was interacting with and causing variation that wasn't real. It wasn't really salt that was changing in the bags. It was the measurement system. So think about that. Go out and do a study of your own. Find out where in your process could you improve your measurement system. Where is the measurement critical where you have to get the right result? And then go find out if your measurement system is giving you the results that you need.